Hello everyone, and welcome to the Coding Club's official review rounds for Calculus 2 or Math 114. This is going to be a brief summary. I'm not going to go into too many details. I'm going to explain the general idea of the lesson as simply as I can. Calculus 2 is something that I feel like you shouldn't overcomplicate. Don't stress about it. It is a fairly straightforward course. You have a set of rules, you have a few formulas, a few concepts that if you understand them and then you just apply them, you will get the answer 90 to 95% of the time. And for the last remaining 5%, you just need to think creatively because the answer is there, but it's going to be a bit hidden. For this review, I'm going to be going over my personal notes that I took throughout the spring 2024 semester. I'm also going to be using Dr. Ibrahim Awadallah's notes as backup. You will notice that the notes are similar. However, my notes are significantly shorter and more compact, and I would also strongly recommend that when you're studying, after you have understood the concept of the lesson, after you have grasped the general idea, that you would go to the book, which you can rent out from the library or check on your Blackboard, it's going to be there, to go to the lesson that you're on. If you would like to read the book's explanation of the lesson, that is incredible, you should do that. However, if you'd like to skip straight to the questions, you are also able to do that if you want it in a much more, let's say, efficient way. You can have the explanation by the professor or through this video, and then you can skip straight to the exercises. I'm not going to be going over exercises just because I feel like this is something, it will take a lot of time in the video, and I want to keep this video short, compact, and concise so that you can watch it and just use it to refresh your memory, whether it be you're watching before a midterm or a final exam, or you just want to get a heads up and you're browsing the Coding Club's YouTube and you came across this video. I'm going to keep the video fairly compact and short. The book is mentioned here. For the answers to the book, there's another PDF that you can find, which is the answers to all of the exercises in the book. Now, to start with, calculus has, let's say, three main parts. Calculus 2. The first part is going to be integration. The second part is going to be finding the areas of parts of the graphs. So that would be calling it improper integrals, or using the different methods to find the area within a 3D graph. Once we get to that lesson, you will understand what I mean. And the third part is going to be about series, infinite series, how to find if they're convergent or divergent, how to find their values, the various different tests and methods that we use to determine if they are converge or diverge. And then there is a very small part at the end of Calculus 2, which is about parametrization, which is just thinking of a graph in a new way. If you're coming now fresh from Calculus 1 and you haven't had a lot of experience with calculus in high school, parametrization is a very simple and straightforward lesson. It just teaches you to think in a different way. It's the same equation. You're dealing with just the same regular old calculus that we always deal with, but you're applying new principles. You are looking at the same object, the same concept through a different telescope. So it just needs a bit of critical thinking, a bit of just critical thinking and focusing, and you will be able to understand the idea. Now, to begin with, I'm going to assume that you have basic understanding of Calculus 1, the integration technique, the differentiation technique, and a good amount of the rules that have been proven in Calculus 1 lectures. So let's start with 5.5, integral and substitution method. These rules, the professors may choose to prove them. They may choose to just tell you to accept them as they are. If you would like to pause to take a screenshot, if you would like to prove them on your own, that is something that I encourage. You should do that so that you can understand why we accept these rules as they are and just implement them without manually solving every time. This is ln of 3. Now, you have a few more rules that you have to go over. It's just anytime you see or you recognize that a question has one of these, you can instantly resort back to the formula and just know that, yeah, this rule, if you have, for example, tan of 5x, then you would know instantly the integration of tan of 5x dx is going to be negative integration of negative sine of 5x over cosine of 5x, which in turn is going to be the negative natural log of the absolute value of cosine of 5x plus c. If you jump from tan 5x to the last step, the professors should have no problems with that because they have proven to you previously that this is one of the rules and formulas that you just need to know and have essentially memorized. Now, it's not realistic to say that you need to have all of these rules memorized, but just with practice, if you solve 20 or 30 questions before a big test, or let's say 20 or 30 questions every week before a big test, you will be able to recognize these and they will become second nature. You'll be able to automatically tell that, yeah, I recognize this question as a as that's the answer for it. Now, this lesson has, let's go to the professor's notes here. He goes over why everything is the way that it is, and then he gives you some examples. Now, I'm going to skip the first lesson and the lesson after it because, again, it's just rules that the professor is going to be explaining throughout the hour and a half or hour and 15-minute lecture. And I'm going to keep this in the interest of keeping the video compact. I will just have those first two lessons be, I'm going to assume that you understand the basic idea of them and that you have the rules memorized so that you can apply them in the next lessons. So these are some of the examples that the professor has been solving. So here you can see that you have the integration of the square root of an expression. You are differentiating the expression underneath. You are finding it in terms of y. You're changing the graph from x dx into y dy so that you can have a simpler way, and this is called u substitution, or in this case y, because you're substituting with y, to solve it so that it is in a form that you can integrate directly, which is the integral of the square root of y. You can take the half outside just as the professor did here. He goes over more expressions. So here, secant squared of 5t plus 1 times 5. Same thing, it's going to be present in one of the rules, which is right here, secant squared. It's not going to be the same. He added a 5x plus 1 inside, and then he multiplied the whole thing by 5. So you can just continue. You need to think critically to understand what is going to change, but the base is going to be the same. You're just going to apply one of these 18 rules to solve all of your problems. They're going to be fairly straightforward, but some questions will have you think in a different way to be able to solve. What he did here is, again, with u substitution or y substitution, he turned the entire expression into y, and then he differentiated it. And the question is phrased in a way where the derivative will have a divided by 5, so it's going to cancel with the 5 above, as the professor did here. So you're going to end up with secant squared of y, which is the same as secant squared of x. So you can just instantly integrate it into tan of x, or in this case tan of y, but at the end you need to make sure that you turn back the y into what it was originally, which is 5t plus 1. So you would take that and put it back here, because the question started in terms of t, so it has to end in terms of t. This lesson is fairly straightforward. The professor goes over more and more examples of it. I'm not going to bore you with the details. I would strongly recommend that you go over examples from the slides or the professor's notes, from the book. You can choose any of these to solve them. If you would like to solve a bounded or an unbounded integral, that is up to you. You're going to have various different types of questions. I would recommend that you solve at least 2 or 3 of each type, But if the professor is focusing on only one category of questions, that's also your call. If you want to spend time with solving questions for types of questions that didn't come, like graphed questions. It's still the same concept, the same method of solving, it's just phrased in a different way. Now let's move on to 5.6, which is the bounded substitution method. It's the same thing as the previous lesson, which is just substitution method, but now it's going to be bounded. Now you're going to have, instead of it being unbounded, it's bounded. What does it mean when an integral is bounded? It means after you're done differentiating, integrating, instead of it being in terms of x, or in terms of a variable, in terms of an unknown, it's going to be in terms of the things that have been given to us. So this would be, so let's say you have this from 5 to 3. So this would be secant inverse of 3 minus secant inverse of 5. And there is not going to be a plus c. You only put plus c's when it is an unbounded interval to account for the part that is going to disappear when you differentiate it and go backwards. Let's not get into that though. So bounded substitution method is the same thing as 5.5, but you are putting now values so that you have a final answer that is a number. If you have, and the good news with this is 9 times out of 10, your calculator can solve this on its own. Just make sure that you put the syntax and the parentheses as correctly. The calculator will give you the right answer. I would recommend using this to double check your answer after you've solved, or as a Hail Mary if you're trying to score a bit of extra credit and you don't know how to solve on the test. You can put it on your calculator and just hope that you get partial credit. But you should know how to solve this. Now, that was the basics that have carried over from Calculus 1. Now getting into the new parts, which is Calculus 2, you're going to be focusing for the next few lessons on graphing and using integration to find the area or to find the volume, because it's going to be a 3D graph, to find the volume of different shapes of graphs using various methods. But you have to keep in mind, at the end of the day, you're going to be using the same principles that we previously discussed of integrating various different formulas and various different functions. So, volume using cross-sections, as well as the shell method for this lesson. So, what is a cross-section? A cross-section, very simply, is a part of a graph that has an easy to define area. So if you have, in this case, this cylindrical graph, you can use the area you can use the formula to find the volume of a cylinder, which I'm not going to bother Googling. The formula exists, but what you need to know is that the simpler version of that is to find the area of a circle, which we already know. What is a cylinder if not a large number of circles stacked on top of each other? We don't know the volume of a cylinder, but we know the area of a circle, which is a lot easier to calculate. And what you're going to want to do is you put that in your a of x, which is just the area of the function x of the circle, and then you just integrate it from a to b, so you're finding the area of all these circles stacked on top of each other. And if you do the integration as bounded and you use a method that gives you a very accurate result, you will get a very accurate answer for the volume of the cylinder. Assuming you don't know the equation or formula for the volume of the cylinder, you can use the area of the circle and integrate that from a to b to find the volume of the cylinder. Now, here we have this pyramid shape going from 0 to 3 on the x-axis, or on the z-axis if you want to look at it as a 3D shape. You can do that with this line here being the z-axis. Now, what is a pyramid if not as stacked squares on top of each other? Or yeah, we don't know the volume of the pyramid, but we know that the pyramid consists of a large number or an infinitely many number of squares stacked on top of each other. And we know what the area of a square is. It's just the side of a square multiplied by itself, which is just x squared. And since we know the height of the triangle or the pyramid, we know the interval on which it lies. The tip of the pyramid is at x0 or 0, 0, 0, and the bottom of it lies at x or z3. So you know that the interval is going to be from 0 to 3, and you use that as your bounded, as your interval for your bounded integral to find the exact number for how much volume the pyramid has. Now, this is what I was talking about earlier. The abstract, the vision here, is that you're dividing a shape into many small areas that you can find the area of, and then integrating those areas from the start of the shape, from one end of the shape to the other end. By definition, volume is the integration of areas, so the shape can be divided. So if you can divide the shape into easily, and I'm using this word here, areable shapes, as in you don't know how to get the volume of the pyramid, but you know how to get the area of the square, and a pyramid is just an areable. A square is a shape you can find the area of fairly easily, so you're using that to get the volume of the pyramid. Now, disk method. Disk method is usually, yeah, as present here. Disk method is when you have a function. It does not matter what the shape of the function is. You can have any function like this. You can have a function be like this. As long as it revolves around an axis, it can also be done like this. It doesn't have to be about the x-axis. As long as the function revolves around an axis to form a shape, I'm trying to mirror the graph here, but not working very well. As long as it revolves around any axis, it's going to form a shape that can be easily areable, if you want to use that term, into something that is easy to find the area of, and then when you integrate from the start of the shape to the end of the shape, you'll be able to find the volume. We know that the area is going to be pi r squared, because the area of any point is going to be a circle. It doesn't matter where you are in the graph. Let's say you're at this point in the graph, it's going to be a circle of varying heights or varying radiuses. How do you know what the radius is? The radius is the function. So depending on where you're at in the function and what value you've set for your function, that's going to be your radius. And you're going to just want to integrate that from a to b, from the start of the shape to the end of the shape. Pi is a constant, so you can take that out and just integrate f of x squared dx. Now, let's talk about a circle, a sphere rather. We don't know how to find the volume of a sphere. There is a set formula that you can just Google to find it, and that's going to be your final answer. If the question is, what is the formula for the volume of a sphere? But assuming we don't know that, we only know the area of a circle, what we can do is we can consider a sphere as infinitely many circles stacked on top of each other to eventually form the sphere, and we just integrate from minus a to a, from here to here. Now, what is the question here? The circle x squared plus y squared equals a squared is rotated about the x-axis to create a sphere. Find the volume. So you have this as your function, and you want to find the radius. You want to find, the volume, using the idea or concept that we discussed a few minutes ago, which is you want to find the height. The height is the only thing that's going to change. If you want to take it as half of the height or the entire height, that's up to you. It doesn't make a difference. So you're going to want to rewrite the formula to be in terms of y, because y equals fx, right? And we're trying to find the integration of fx squared dx pi. You can take the pi outside, it's the same. So you need to rephrase the question to be in terms of y. You can just move around the circles, the variables, to get the equation of y, and since it's a square root of a root of, since it is a squared square root, it cancels out, so you're left with this equation. And once you simplify and integrate again, we're just integrating using the basic integrating rules that we were given in 5.5 and 5.6. You are left with this. And this, if you search up on Google now, this is the equation for the volume of a sphere. Yeah, 4 over 3 pi r cubed. Here we're using a as the radius of the circles within the sphere. Now, the next method we have is the washer method. The washer method is similar to the desk method, but the difference is that you don't have it, the radius is just going to be slightly harder to get. Previously, the radius was very simple to get. It's just going to be, let's use this shape, it's easier. Let's erase these so you're not confused. The radius is always going to be from the center axis to the edge of the graph, and then down again. But what if, sorry, that's the circumference. The radius is from the middle of the graph to the edge of the graph. But what if I don't want, what if this isn't my only part of the graph? What if I have another circle within that, and I want to find the area between these two shapes? So you want to find the area here. So your radius would be the big R minus the little r, which we'll go over now. So here you have two cylinders stacked on top of each other or within each other, and you want to find the radius of the shape between the inner one and the outer one. If you subtract the bigger radius from the smaller radius, you get the radius that you want. Another way of writing this is going to be, so the formula for this method is going to be volume is 2 pi integration of RR, which in this case is going to be, this is 2 pi r squared. But since we're talking, sorry, this is 2 pi r y, because this is going to be talking about the height of the shell, and this is going to be the radius. R is going to be after you do r minus r. That's the radius we are looking for. So what you do here is you're going to calculate volumes that look like a volcano, essentially, because you have, this looks like a volcano if you were to just view it creatively, let's say, using graphs using rectangles. Because this, if I move it, I don't know if I'm going to be able to move it. Let's use this. If you rotate this shape, I don't know how to rotate the shape. Alright. If you look at it from a different perspective, from a 2D perspective, your cylinder is going to be a rectangle. So you're going to use that, you're finding the radius, the area of a rectangle, which is xy, to find the volume of the shell by using infinitely stacking rectangles. That is the concept here that we're trying to, that's the idea that we're trying to achieve here. Now let's go for this graph, which might clarify the idea a bit. Your final volume, if you think about it in a different way, is you can do the integration twice. Once for the big shape, and then again for the smaller shape that's inside, and you're going to subtract them from each other to find the volume that we want, which is the volume that's here. You can also choose to do that. So the V total is going to be the big volume minus the small volume, which you get very simply. You're just finding the volume. This is going to be the cross-section method. Using cross-sections, you integrate using the area that you know, the shape, the areable shape that you already know previously, to be able to find the volume of the graph. Here the C in the final formula, you're going to have C, which is 2 pi r, the circumference of a cylinder, times the thickness, times the height. This gives you the final answer of what is the volume of the cylinder, is represented by this graph. Now moving on to arc length. Arc length is a lesson that just is a very basic and straightforward formula that describes how we can get the length of a line on a graph, or the length of an arc, which is a collection of lines. So suppose you have this graph on the x and y plane, and you have, let's say, this line. You want to figure out the length of this line. What would you do? How would you break it down? You would be able to this would be easier if you broke it down into smaller lines that are mostly straight, and you can use the formula for the length of a line, the distance between 2 points formula, which is the square root of delta x squared plus delta y squared. So if you apply that principle to a line that isn't straight, you can find the length of that line by finding the difference in all these tiny small points on the graph. So how do we get to this formula? How did we get to the formula you can see below? Well, if you have the collection of all of these lines, the formula for the distance between two lines is going to be the summation of all of the different values of delta x1 and delta y1. So instead of writing this all out, we can put it all in a summation as k, which is the subscript. You're going to take summations a bit later on in Calculus 2. You'll understand what this means. But a summation is just a shorter, more compact way to describe a very large value, which is something plus something plus something plus something that has that something in common. So instead of having to write it all the way out, because you can see here there's a common term, or there's multiple common things in this formula, which is the fact that all of them have square root delta x plus delta y squared, delta x squared and delta y squared. The only difference is that the little subscript here changes. Delta 1, delta x1, delta y1, delta x2, delta y2. So how do we account for that change? We substitute it with a value of k, and we say from k to n. So this is going to be from delta x power of 1, since we're starting at k equals 1, up until we reach n. N can be however many points you're going to have on the graph. In this case, since we're going to be trying to get it as accurate as possible, we set it as close to infinity as we can. So you summation, you create the graph as such, and then you can take out delta x. Why do we want to take out delta x? You'll see why in just a moment. You take out delta x as the common term. You have delta x squared all under the root, the square root of delta x squared into 1 plus delta y squared over delta x squared. Now, does this make sense? It should. If at any point in your entire time studying Calculus 1, you don't understand why something is, why this formula came to be, or the reason for applying this formula in this situation, you need to take a step back, pause, and understand why we are using this formula so that you can get a better grasp of the math behind it, because calculus at the end of the day makes sense. Math at this level should make sense. You should be able to visualize the graph. You should be able to understand why we are using certain formulas. So to check if this formula, or if this factoring the delta x out makes sense, add it back. Add delta x squared back into the brackets. You will get delta x squared plus delta y squared, delta x squared, and then you can just cancel the delta x squared. You are left with the original formula, which is delta x squared plus delta y squared. Now, why are we doing this? We're doing this because we want to take delta x out of the equation. Since this is the square root of delta x squared, you can cancel the square root with the power 2, and you are left with delta x on the outside. And now you can drop the brackets and just have it as 1 plus. For now, you can ignore why this is f prime of x. Consider this as delta y squared over delta x squared. Now, what is delta x? Delta x is just dx, because it is delta x, and when you are saying dx in algebra and calculus in general, this just means a small section of the graph. What dx means, it just means a small section with respect to x, and if it's dy, it just means a small slice of the y plane. That's what that means. So you can interchange it, since in this case, logically, you are just taking small points along the x-axis. They are interchangeable. Now, why is f prime of x equal to y squared over x squared, or delta y squared over delta x squared? So, you have a function, right? This is a function. This is a line. A line is represented by a function. F of x equals, what does it equal? Usually it equals y, right? Because this is f of x is equal to y. We have that as a formula. We have it memorized since grade 8 or 9. Now, what happens if you differentiate it? If you find the derivative of x, f of x prime, with respect to x, you essentially just found dy over dx. And we agreed that dy or dx is just another way of writing delta y and delta x. So we know that f prime of x is just minuscule changes of y divided by minuscule changes of x. So we can just replace that in this part, because we don't want to find the difference between 2 points every time. We can just differentiate the function, square that, and then you have your infinitely many differentiations between the small slices of x and y. So we replace that, and since it's delta y squared and delta x squared, we just put both of them in parentheses and we add a squared sign. So now this is equal to this. Why do we do that? Because another neat function in calculus is the fact that a summation can be used as an integration. A summation is in essence integration, because when you think about it, you are differentiating, like we said on this graph, you are differentiating this line, right? Sorry, you are integrating this function. Integration is just the area under the graph, is it not? So another way of writing the integration, or another way of expressing when something is an integration, is in this particular case when you are taking it as the summation of multiple points. So these small points that we agreed we're going to slice the line into, you are taking the length of those points as sorry, not area under the graph, the length of the lines themselves. So when you are integrating that with respect to dx, you are finding the area of you are finding the length of the arc. And you can do the same thing with x, and you can do the same thing with y if your graph is something like this. You can just swap from integration from a to b with respect to dx to integration from c to d with respect to dy. That is the core of the arc length lesson. It is very simple because the questions in the exam are just going to come as you have a function, you have a graph that is expressed to a function, find the arc length from 2 till, let's say, 7. What you do is, if the graph is with respect to x, you can just find the integration from 2 till 7, and since this is the only item that's going to change from different questions, it's just what the function itself is going to be. So you differentiate the function, you put it in square root, you square it, no, you not square root it, you square it, and then the rest is just math. It's just simple algebraic expression. You are simplifying it, and you are done. That is the whole lesson. There's nothing else to this lesson. You differentiate the function, and you put it in this formula. But I have spent the last 10 minutes or so explaining how this formula came to be and why you need to understand the behind the scenes. Why does this make sense? because nothing in calculus is just take this formula and apply it. You need to understand why it works. And this is why it works. So the next lesson is surface area. Surface area is very similar to the arc length lesson, but instead of finding a line, let's say, expressed as a function, or this line, you are finding a summation of all of these lines expressed in a geometric 3D shape. So picture this as a lot, hundreds and thousands of lines all stacked right next to each other. You are expressing that, you're finding the lengths of all of those, the areas of all of them, and you are adding them up. So, assuming that the thickness of the shape itself is negligible. So, what are we doing here? The surface area, you need to understand this as a lesson, is the circumference of the shape, whatever shape it is. So this is going to be the circumference of the shape, multiplied by the length of the shape. It will get you the surface area. If you multiply the area of the circle or the shape, you will get the volume of the shape. But since this lesson is going to be the surface area, you are multiplying simply by the outside of the shape. So this is a circle or a cylinder, whatever shape it is. It doesn't have to be symmetric, it doesn't have to be straight lines. The varying circles, you are just calculating the circumference of that circle at the point x, because this is going to change. At one point your graph may appear to be something like this, for example. You are calculating the circumference of that shape at the point x, and you are multiplying it by the length of the shape at varying points as well, with respect to x. So the formula is very simple. We just talked about the formula for the arc length. You take the formula for the arc length as it is, and you bring it down here, and you just multiply it by the formula for the circumference of a circle, or any the circumference of a circle where the radius of the circle is the varying different heights of the, or the varying different radiuses of the shape. Since we know that r is, in this case, the y value of the shape, which we know as y equals fx. We just described and we just proved that y is fx. Our whole system is based on the fact that y is equal to fx. So since y is equal to fx, we can also say that r is equal to fx. So 2 pi r, the formula for the circumference of a circle, we can also say it as 2 pi f of x. And once you multiply that by the length, you get the, obviously as the integration of the circumference multiplied by the length, you get your surface area. Okay, this lesson is also very simple. I would just recommend doing your web work assignments and solving a lot of practice questions on it. The essence of the test, the questions are in the exam are going to be the exact same as for 6.3. You are just going to be given a function. All you need to do is just differentiate it, and you can plug this into your calculator to double check your answer. But the test, if you are taking with Awadallah, Dr. Ibrahim Awadallah, you are most likely going to be asked to show your work and simplify it as far down as you can, until at the very end, if you can't simplify it any further, you can just plug it into the calculator and give him the answer as calculator. So the next lesson is work. Now, I am not a big fan of this lesson, because if you have taken work in physics, you will know that work is just, we know it as force times distance. Force exerted over a distance, that's work. But you need to also learn how to express it in terms of math, in terms of calculus. We know that if you were to graph a function for whatever value of work you are doing here as time, this is delta time, and this is your work, if you are expressing, you're doing, let's say, more and more and more work over time, the work you are doing is expressed on the y-axis, which we agreed that y is equal to fx. So the force you are exerting is in reality expressed as f of x. It's a function of x. And the distance that you are doing it over is just going to be the small, what do you call it? The small slices of the time interval that you are doing the force, that you are exerting the force over. So another way to express this, this is expressed in terms of physics. You can express it in terms of calculus as this function here. You express it as the integration from a to b of f of x. Very simple. Now, there is something in physics called Hooke's law. Excuse me just a moment. There is something in physics called Hooke's law, which is, it's also very simple. It tells you that the force is equal to the coefficient of friction multiplied by, the force constant k, or the coefficient of friction multiplied by the distance across which the object has been moved. This is a very basic law as well. You should have taken this in Physics 1, if you remember this from Physics 1. So very simply, we're going to use this law to express force if force isn't expressed as a simple function. So if you have a word question, as such, the solving would be as follows. You are just going to use the different keys, the different values that the question has given you, such as a force of 24 Newton holds for a length of 1.8. You're just going to be a bit creative. You're going to get a bit creative to find the answer. You have all, in all cases, you are going to have all of the information that you need to be able to solve it. It just may not be given directly. So in this case, we have it expressed as, for part B, work required to stretch to 2 meters. So the work required to stretch it to 2 meters, since we don't have a function for force, we express force as the product of k and x. But since we don't have k, we calculate it in as such. So we get k, we get x, and we find the answer as such. It's also a very simple lesson, and you should be able to remember it from Physics 1. So we're not going to spend too much time on it. I wouldn't worry too much about this lesson. It's also mostly straightforward. Now, the next lesson is Exponentials and Logarithms. This is mostly just revision. You have taken this in Calculus 1, you've taken this in high school. I'm sure all of you remember these rules. But if you are a bit rusty, here are the most common exponential and logarithmic properties, let's call them, or rules. For if you want to pause and take a screenshot, you should do so now. And here are the rules for the derivatives and for integration and u substitution, as well as the logarithmic rules and derivatives as a function. The derivatives of a function that has logarithmic and or expression of exponential expression, as well as the integration. So this lesson is just going to be when you're going to be solving questions in it, and however the professor explains it to you. This lesson is just practice for you. You should focus on this lesson just to get more familiar with the practicing of creative problem solving, of how you should approach a question mathematically. There is no concept here to grasp. If you would like to search for a concept, you just try to prove all of these questions. The proof of them is simple, but it takes a bit of time, so we're not going to cover it in this video. All of these equations can be proved arithmetically, mathematically. There's multiple different ways to prove them, but in this case you can take them as a given, because the proof doesn't help you understand the concept in this particular case. If you would like to seek out the proof, you are more than welcome to do so, and it will help you to some extent. But these are, when you're solving problems, you're just going to be you're going to familiarize yourself with them and memorize them subconsciously. Here are also some rules for integration, and yes, and that's the whole lesson. Now, next up, we have the lesson of Differential Equations, 7.2. And this lesson is pretty fun, if I'm being honest. If you recall the lesson 5.3, I believe it was. No. From Calculus 1, there was a lesson called Implicit Differentiation, which was 3.7. This is the same concept, but you are doing it backwards. So you are separating x and y in terms of dx and dy, and you are integrating it to get back to the original formula. Here it is as an example. So you have dy over dx. You want to keep y on one side and x on one side, and then differentiate both sides as each on its own. So here you can see that we have y and x on one side, and we also have y and x on the other side. So we're trying to separate them so that we can integrate both sides with respect to the variable found on each respective side to keep the system true. Because if you try to integrate this value here, it's going to be difficult to integrate, because what are you integrating it with respect to? Or if you multiply by dx here, the integration of 1 plus y e to the power of x dx is going to be difficult to integrate, because you have two variables. You're going to be integrating, and it's going to be a bit annoying and difficult to do because you have two variables. So the whole concept, the whole idea of this lesson is to just separate the variables to each side and then integrate both sides. The lesson itself is also very simple. This is mostly just going to be problem solving questions, practice until you get the hang of it. There might be some difficult questions with trigonometric functions, but just solving them and practicing on them, you will get the hang of it within 5 to 10 questions. You should understand the main concept. Now, the next lesson is also just going to be rules or equations, something that is true. This is a hyperbolic trigonometric function. It is similar to just a normal trigonometric function, but you are multiplying by h in all of them. So this is sine h, cosine h of x. The teacher may express it as sinh or cosh or tan h as such, and you just need to know that they are equal to this. Your professor should prove it quickly in class, should express the way it is proven, but frankly, this lesson doesn't hold that much weight if memory serves. This lesson does not hold a lot of weight in the midterm, and it will not be present again in Calculus 2, and it will also not be present again in Calculus 3. So my advice is to just understand this or memorize this as is, and get comfortable with differentiating it and integrating it. There are also some identities. There is a very small difference between the trigonometric identities and the hyperbolic trigonometric identities. So the x and tick are just if it is the same as the normal trigonometric identity, or if there is a change in sign. So cosine of h squared plus sine of h squared of x is equal to 1. If you recall in lesson, I believe, 3 point something, as well in Calculus 1, you took the trigonometric identity, trigonometric identities. It was in 1.3, I believe, yes, Calculus 1, 1.3. In Calculus 1, 1.3, this function would be cosine squared of x plus sine squared of x equals 1. So you need to be very careful with the pluses and minuses, because the professors that's the whole gist of the lesson, is that it's trying to trick you with the plus and minuses. So if you pay close attention to that, you will be good to go. There's no other tricks in this lesson. Just pay close attention to the plus and minus and you'll be golden. Same thing with the derivatives of inverse trigonometric hyperbolic functions. Or as such, these are also rules that you can just write them down. And if you see them present in an equation, you will be instantly able to resort back to this page and solve it it's going to be the exact same. There's not going to be any tricks. The only difference is what the value of x is going to be. So if it's going to be x, you keep it as is. It's going to be 6x squared. You're going to put it as 6x squared, and you're just going to adapt and solve accordingly. Now, the next lesson is integration by parts. This is, frankly, it's an interesting lesson, and you have to pay a bit of attention to it because it builds on the product rule that you took in Calculus 1, towards the end of Calculus 1. So we know that the derivative of f of x times g of x is f of x g. So this is the way I have it memorized, is fg is equal to fg prime plus gf prime. You can have it memorized however way you want. You can come up with a creative mnemonic device, but this is how I have it. This is the derivative of. This is how I have it memorized. Now, if you are integrating both sides, you're integrating this and you're integrating this. What are you? You're integrating every term, not every side. What do you get? So the integration and the derivative, since they are opposites, they're going to cancel out. So we know now that f of x g of x is equal to the integration of f of x g prime of x plus g of x f prime of x. Now if you take this to the other side, you're going to get the formula for the integration by parts, which is f of x g of x minus the integration of g of x f of x prime is equal to f of x g of x prime. You just arrange it a bit more just by swapping sides. You're going to get this. Why do we need this? And once you rename it, you're going to have it as derivative of u dv is equal to uv minus the integration of v du. Why do we have this? Why do we need this? Because sometimes you're going to get the integration of a function multiplied by the derivative of that function. And you can try to solve it by other means, and it is possible using other methods, but the most efficient and clear way to solve it would be with integration by parts. Why is that true? Because you're building on the product rule to simplify it, to break it down into something that can easily be calculated. So if you cannot calculate the integration of u dv, you break it down into uv minus the integration of v du. Now this, 90% of the time, this is going to be instantly calculatable, or you can easily calculate it. There is a small percentage of times where this is not going to be calculatable. You're going to have to break it down further to get uv minus, and then you break it down again to get vu minus the integration of u dv, something along these lines. And now this should definitely be easy to integrate. Now let's look at an example to understand the concept of this. Delta x, the integration of x times cosine of x delta x. Now you are going to take u as x and dv as the cosine of x, so that when you integrate it, you are going to get the formula as follows. And this is just the way that I have it laid out. It's always going to be u dv duv, and this is going to be the formula. I have this as this is just the way, this is the mnemonic device that I came up with to remember it easier. It's going to come to this shape. You're going to go here first, and then you're going to go here first, but before you go there, you add a minus integration. This is just a way that I have it so that I can memorize it a bit easier when you are laying it out. Now you apply the formula, and since you cannot differentiate, this was to backtrack to the point that I mentioned previously, which is that you're not going to be able to differentiate this, but you're going to be able to differentiate this much easier. If you lay out the terms, you can't differentiate x cosine of x delta x, but you can differentiate sine of x delta x. This was one of the rules mentioned previously in 5.5. Let's go up quickly. In 5.5, the integration of sine of x is minus cosine of x. So if we go back down to, sorry, where were we? 8.1, yes. If we go down to sine of x, this is going to give us minus cosine of x plus c, and minus minus, you can just replace that with a plus here, because there's a minus before it. Then now you have your final answer for the integration of x cosine of x with respect to dx. Now, sometimes you're going to have to get just, this is as blunt and as straightforward as you can get. There will be lots of questions where the only way to solve them is with just trial and error. You want to take one term as u and another term as dv and just try solving it. If you have gone through a cycle multiple times, you know how here I told you this may need to be broken down into into u dv, u minus integration of dv. If you are repeating this cycle a lot of times, then pause and go back to the question and change your, this is u, take it as v, and this is dv, take it as du, and try to change it, or take this as dv and take this as u. There will be some questions where you're going to get frustrated and not know which term to take as u and which term to take as dv. There is no formula, there is no straightforward way to know which term to take as which. You with enough practice, you will just be more comfortable and you will have just a gut feeling. Your brain is going to do the math faster than you can comprehend it, and with time and enough practice you will be able to know which term to take as dv and which term to take as u. If you take one and it turns out that your gut instinct is wrong and you're just repeating the formula multiple times, swap your terms. Go against your gut instinct and change the terms and solve it. Eventually you will come to a conclusion. There is no other concept in this lesson. It's just math, it's just solving it. Here are a few more examples that you can go over. I would strongly recommend that you look up some sample problems online, or you take the book from the Saqr library. There's a few copies of the calculus book, and you solve some questions on it there. It's very helpful, and it tells you what small sort of tricks to look out for when you are solving. Now, there is something, this is the formula for a higher power trigonometric. So when you have the integration of cosine to some degree n multiplied by derivative of x, you can break it down further into this, what seems like a monstrosity, but after it's been proven, it really is not that complicated once you understand why this is equal to this. It's the same concept as integration by parts. You're applying the same idea, you're applying the same formula to it to simplify and get the value of n lower. Now, if the value of n here was, let's say, 5, this is going to be 3. So you take the value of 3, you still don't know what cosine to the power of 3 of x. You take cosine to the power of 3 of x, the integration of that, you plug it back in here. So now this is 3. Now this is going to get simplified a lot, and you're going to get it at the end as the integration of just cosine, or cosine to the power of 1, which we know what the integration of cosine of x, if you go back to 5.5, you know what that is, so you can just solve it instantly. So you may be needing to repeat this cycle multiple times until you eventually get to a point where you can differentiate the integral at the end. There is proof for this. If you want to look it up, you can. It's about, I think, 2, maybe 3 pages of proof to do the integration by parts. It takes a bit of time to get to this final formula, but you can choose to just memorize it. I just have it memorized, and it's a lot simpler. It saves a headache. Now, when it is bounded, it's going to be the same thing as unbounded, but at the very end here, you are just going to be taking the bounded of that term. So if this is a to b, this is going to be at, b and a, and then from a to b. The same formula, the same concept, but if it's on a bounded interval, you are make sure to account for the bounding. And if it's a bounded interval, you don't add the constant of integration plus c at the end, because you have the formula, you have the values for which you are integrating. Now, lesson 8.2 is also just more rules and more algebra. You just have to understand that the integration of this equals that. Why that is true, you can resort back to Calculus 1, you can look up some proofs online, or you can just take it at surface value, at face value, and just understand that the integration of sine of x is equal to minus cosine of x. You can just understand that and memorize that as is, and you will be getting hopefully a good grade in the quizzes. But what I encourage, if you want to understand why that is, look up some proof, but in the interest of keeping this video relatively short, I'm not going to be going over the proof of every trigonometric formula and trigonometric integration. So, when you are integrating trigonometric integrals, when you are integrating trigonometric functions, you're going to have three cases. If you're integrating sine to the power of n multiplied by cosine to the power of n, that within itself splits into three cases depending on the values for m and n. And if the values of n and m, anything other than, if they are something other than both of them being even, you are going to be using the substitution method to solve. But if they are both even, if you remember, even is evil, odd is good, that phrase Professor Awadallah likes to use that a lot, and it's very fun to remember. Even is evil, so when it is even, it is identity. And we don't like identity because it's just a lot of memorization. It is a lot of just understanding that this is equal to that. Don't ask questions. So, moving on to the other cases, and we'll go over some examples of case 1. Case 2 is when you have secant and tan. Regardless of what the values of n and m are, you're always going to be using identity to solve them. You are going to be finding one of the trigonometric identities that were mentioned previously in 1.3, I believe, to solve for this. You're going to simplify it, and then you're going to solve. And if it so happens to be that after you have simplified using identities, that it simplifies to one of this, to this case, then yeah, you can go into the case of is it even or is it odd. This lesson is also, like I said, it's mostly math. There's no concept to grasp. This is just, they like to train you to understand that let's solve mathematically, let's get good at algebra, let's get good at calculus, Case 3 is when you have differing coefficients for a and b. Now this is just a formula that you have to take at face value. You can understand the proof of why this is with identities. This can be proven with identities, but when you are solving it, and this is all the integration of, you get this value. It's very simple. This is the best case, but you just need to memorize when it is plus, when it is sine and cosine, and when it is a minus b, and when it is a plus b. You memorize these values and you're going to be good to go. These values are not interchangeable. You cannot mix up between this group of trig functions and this group of trig functions. These are, let me do it in red, these are not interchangeable. You have to make sure you know when to use sine and when to use cosine. An easier way to memorize this is that this is always a minus b, and this is always a plus b. If it is sine cosine, it's going to be sine sine. If it is sine sine, it's going to be cosine cosine, and if it's cosine cosine, it's going to be cosine cosine. And with plus minus plus, you can just memorize it as plus minus plus, as alternating signs. And then obviously the whole thing is going to be in to the power of, multiplied by half. Now, solving with some examples, you can see why the solving is the way that it is. You are taking sine cubed, which is an even number, which is an odd number, sine power 3, so this is odd, and this too is even. So when you have an odd and an even, when this is sine, So m is odd and n is even. This is the case we're at. We're going to use substitution. What do we mean by substitution? We substitute, we multiply, we expand, sine to the power of 3 into sine to the power of 2 times sine, and we use substitution. We substitute y to become x. Why are we doing this? Because we want to get everything in terms of y. Everything in terms of sine. So we do this, you differentiate it, now you have substituted cosine of x and cosine of x and dx with y's, with dy and sine. So now we can substitute this value in here. Why are we doing this? To simplify it further, because there is no other obvious way to solve this question. Once you have simplified it, you can notice that the cosine that we have taken and turned into this formula, this is equal, they are equal to each other, hence the substitution. You are substituting one in place of the other. You are crossing out sine with sine, and you do that process again. Not that process, sorry, you use trigonometric identity here. We know that sine squared plus cosine squared is equal to 1. So since we have sine squared here, we can just take this term and throw it to the other side to give us 1 minus cosine squared of x. Why are we doing this? You will see why in just a moment. Once you do that, and you have it as integration of 1 minus cosine squared of x y squared, did we not just agree that cosine of x is equal to y? So cosine of x, we can substitute that with y. So now we have 1 minus y squared multiplied by y squared. You throw that into the middle. Now you have this formula, and this is just very easy to integrate. You can integrate each term on its own, and you get your final answer. But remember, the question gave it to you in terms of x, so whenever you're done, you have to return it into terms of x. What is y? Y is cosine of x, that we just agreed what y was. And we are continuing with our solving normally. Now, an example for the tan. This takes a few lines of proof, but at the end it's also very similar. You are breaking it down. You are, with tan, this is n to the power of 0 in this case. So you are taking tan, you're using identity. So tan is tan squared, tan to the power of 4 is tan squared times tan squared. And you take one of the tan squareds and you use the identity to get the equivalent version of it. You take y is equal to tan, and you here in this case you are applying integration by parts. You are applying integration by parts to get to this step, and you take y as tan squared, you differentiate that, and you substitute wherever there is a tan, you substitute y, and you substitute dx wherever there is a dx, you substitute it for what you just got the value of in terms of dy and secant squared. So you get this value here, y squared, the integration of y squared dy minus tan squared. And tan squared, you do the same process again of turning the tan squared into secant squared, and you are going to be simplifying it again further. This is, you can just take this as it is because it's the integration of y squared, very simple surface level. You take the integration of secant squared of x as also just surface value. This is one of the rules that was given in 5.5. You can scroll up and find that. You can take that and you will get the integration, which is just tan of x and 1 as x. Make sure to return everything into terms of x when you are done, because the question started with terms of x, you have to end it with terms of x. Now with 8.3, let's see here. 8.3 is also more just math. It's just trigonometric substitution. It's the same concept. There is no real trick to it. There's no real cheat code to it. You just have to understand and prove why, understand why these are true. And once you have these are true, within a few question solves, you will be able to recognize them in a question and solve them accordingly. So these formulas, you can pause, or I'm sure that you've gone over these in class. Here is an example if you would like to see, and one trick that the professors like to use to explain this is with the right angle triangle, to explain to you, because with right angle triangles you can get more comfortable and more familiar with using, with right angle triangles you are more comfortable with using trigonometrics because you can visualize them. So if you have this as a question and you see the shapes being present, if you see the same formula present, you can directly apply the appropriate equation and then just solve it algebraically. We're not going to spend too much time on this lesson either, because it's just math. There is a method that you can use. This is something that I came up with it. Using the highlighted formulas, use the proper appropriate trigonometric ration, which is one of these. Just recognize that this is equal to, in this case, 1 root plus. So 1 root plus. This is going to be it because it's 1 over plus and there's no absolute value, so we're going to be using this method. Here, what's step 2? Differentiate it to get the equivalent value of d of x, making sure that the integral is in terms of d theta. So once you are simplifying everything, after a few simplification process, you're getting the integral in terms of d theta. Afterwards, simplify it even further if you can, and then just apply the integration trigonometric identity that is given just previously in 8.2, the rules that were here. And you may have a case where after you have simplified it, you're getting one of these 3 cases, in which case you can just consider it as a double question with 8.3 and 8.2. Pretty straightforward lesson, but it's a bit tricky, so you have to be careful not to get confused with what you are differentiating or integrating with respect to. Now the next lesson is a bit of a breather. You can relax with it. It's just one idea that you're playing around it, and it's very straightforward. There's no tricks, there's no confusion, it's very easy to stay on track, and it's very hard to get lost with this lesson. So you can take that as a sign of hope, as a refresher, and something that should make you pretty happy, at least when it's a nice break from all of the rules, and just memorize this as it is and continue with it. So what is integration by parts? This is a lesson that just tells you to integrate the bottom or the denominator of a fraction to create an expression, to create something that is equal to it, but something that is easier to integrate. We don't know how to integrate a polynomial, so we are breaking it down to integrate it as it is. The numerator, we don't know what the numerator is, so you will see in just a moment, you're going to have this as a and as b. As b. So you are factoring the denominator, which is the polynomial, and you are creating expressions. You are breaking it down into smaller mini fractions with a numerator that is unknown. So in this case, x squared minus 2x minus 3 can be integrated into x plus 1 with a numerator of a, we don't know what the numerator is, plus x minus 2 with a numerator of b. So this is the formula. Once you recognize that this is the integration of an unknown over a factored term, in this particular case this is it. If you take the 2 outside, so there's going to be 2 integration of 1 over x plus 1. If the numerator is the differentiated form of the denominator, then the integration of that is the natural logarithm of the absolute value of the denominator. That sounds confusing, but just bear with me. Suppose the term here is 1. This summation is the integration of 1 over x plus 1. Differentiate x plus 1. You will get the answer as 1. So the bottom part or the top part of the fraction is the differentiated form of the bottom part of the fraction. What that means in calculus is the integration of that fraction is the natural logarithm, is ln of the absolute value of the bottom part of that fraction. And that is the whole premise that you are playing around in this lesson. You're factoring it to get miniature forms, to get smaller forms of the original fraction, and then you are just playing around that idea. That is it. That there is no other premise in this lesson. Here is an example. You can see it as in terms of a, b, and c, and then you just multiply to solve this as a system of equations. You solve it as a times everything except what it's on. So it's a times this plus b times this plus c times this. You will notice that you are never multiplying the letter, the unknown, by its denominator. So you are multiplying it by everything other than its denominator. And then you are just solving algebraically. It may look a bit scary, it may look a bit confusing, but once you are actually solving it, it's very straightforward. And then you can just substitute whatever value of x to try to cancel one of the forms. So here I'm substituting x as -1, because I know that if I put -1 plus 1, it's going to come out to 0, and this is going to cancel. So if you have a 0 in any one of these places, it's going to cancel out everything. So now you're getting an equation that has only b and c, or just b in this case, because -1 in this case is also going to cancel out this term. So you have b -1 plus 3, and you will get the answer is always going to be the numerator of the original fraction. I should also point that out. And then you just solve it algebraically, and you get the values for b, a, and c. You plug it back into the original equation that you got with the unknowns, and then you just take them outside, and you will notice that 9 times out of 10, this is going to be 1 over the top part, the numerator, 1, is going to be the derivative of the denominator, which is usually a first degree polynomial. So the answer is always going to have a lot of lns. So that's the whole premise of the answer. This is a few notes as well. You can pause here and read them for understanding some special cases, such as when you should put it as ax plus b, and when you should keep it as just a. This here is, let's say, a quick message of hope. I was originally planning on just gifting this book to a certain individual, one person, but then I figured collaborating with the coding club and making this video would benefit a lot more people. So yeah, okay, moving on to 8.2. Numerical integration. What is numerical integration? It is something when it is used when you cannot integrate it in any other way. So for example, how would you integrate e to the x to the 2 dx? There is no way you can integrate this, and I still remember to this day when Dr. Ibrahim Awadallah first showed us this question. He told everyone in the class, if you can integrate this, you will be getting a Nobel Prize. There is no method to integrate this function. No one knows how to integrate this function. So we are using numerical integration to get as close as we can to a value without reaching the actual value. So ERFI, in this case, if you put it on a calculator or Symbolab or you send it to ChatGPT, it's going to give you this, which is just ERFI, error function that is imaginary of x. It's not a real tangible answer. There's no way to graph ERFI of x. So there's quite a few methods that you can use to get the integration, or to get as close as you can with the integration. The first method is called the trapezoid method. Why is it called the trapezoid method? Because when you have a function, let's say this function. You can graph this function, but you cannot graph the integration of this function. And you are using in Calculus 1, if you should remember, a few methods such as right point, midpoint, and left point methods. This uses the midpoint of the graph. You're going to be losing a bit of information of the graph. This is why this is just an approximation. All of the following methods are just approximations. They are not exact values. So trapezoid method is one of the methods that uses the midpoint. So why are you using the midpoint? You're using the midpoint because it's just simpler. All of the methods here work. There's no reason why you should use one particular method, but unless of course the question asks you to use a particular method. They're all working, but sometimes your gut instinct or the way that the graph is laid out, it would be better to use one method. So if you visualize it, when you have a trapezoid, when you have a function, let's say here, and you are dividing it into lots of midpoints. So let's use these colors here: midpoint 1, midpoint 2, midpoint 3, 4, 5. And let's use yellow to visualize why we have the formula of 1, 2, 2, 2, 2, 2, 2, 1. Because when you are getting the methods of it, you're going to be using the first midpoint once, f of x of 0. You're going to use the second midpoint twice, once for the first function and again for the second function. So this is why we are using, this is why the coefficients are the way that they are. And why am I pointing this out? Because it is a good way to get you to understand or to get you to memorize the functions. You are using to memorize the function. It's just delta x over 2 times f of x naught once plus 2 f of x1 plus 2 plus 2 plus 2. It's always going to be plus 2 until you reach the end when it goes back to plus 1 of x of n. Because the first point and the last point are used once, whereas every other point you can see there is an overlap of colors. So the first point only has yellow, the second point has yellow and orange, the third point has orange and green, the fourth point has green and pink, but the fifth point only has pink. So that is why the coefficients in this case are the way that they are. And you can just substitute this. The function is usually very simple, but there is no particular way to differentiate it. Now, in this particular case, it was the question that the professor gave in the note that I wrote down. It is a differentiable equation. It's easy to do. It's easy to integrate. Sorry, it's an integratable equation, not a differentiable equation or expression. You can integrate this, but to understand and use the trapezoid method, he gave you this as a function. If you plug this into your calculator, it will give you, because this is something you can calculate very easily by other methods, the final answer is going to give it to you as 7 over 3, which is equal to, equal to 2.3333 repeating. It repeats infinitely many 3's. This is why this method is an approximation. Using trapezoid method with in this particular case with 4 subintervals, you need to determine how many sections you are subdividing the graph into, gives you an approximation. It will never, no matter how many, you will have to take it as n equal to infinity to get as close as you can to the answer. But all of these methods are approximations. They are not genuine, and they are not complete values of the answer. That is the downside of using numerical integration. You are getting as close as you can to the answer without actually reaching the answer. Now, the Simpson method is also similar to the trapezoidal method, but it's going to have a few differences in the coefficients and the denominator in here. Let's go back to a different color. The difference is that in the trapezoidal method, it's over 2. In Simpson, it's over 3. And the coefficients alternate between 4 and 2. Why is that? The way that the graph subdivision is laid out, it's also going to be the same thing, and I'm not going to go over why the coefficients are the way that they are in the interest of saving time, because this video has already been dragging on for long enough, and I'm honestly surprised someone made it to this part. but the coefficients are always going to be alternating between 4s and 2s on the condition you would have to make sure that n is an even integer. You are only allowed to use the Simpson method if n is an even integer. That is the premise under which you are allowed to use the Simpson method. And again, very simply, you are going to be solving this you're going to calculate this the way that it is. It's a very simple lesson. There's no idea or concept that you have to grasp behind it. It's just a formula that you are given, and you understand why you're only allowed to use Simpson method when you have an even number of subdivisions, and you can apply it back here. You can use in this particular case, you can also use the trapezoid method, and it will give you a very close similar answer. It will not give you the exact same answer unless you go for a very high even number of subdivisions, but this is just a method to calculate the integration of an expression that is difficult to integrate otherwise. Now, since there is a difference, we know and we have seen that there is a difference between the actual value that you are getting, the value that you are getting from the methods, and the actual exact and precise value that you can get from a calculator or from Symbolab, ChatGPT, wherever you're getting it from. But how do we calculate that value? There are a few formulas in which these are the formulas through which you can calculate the percentage error in the methods. In the trapezoidal method, the T stands for trapezoid here and the S for Simpson. This is the formula through which you have to memorize it. I can't explain why the formula is the way that it is. There is an explanation online, but again, in the interest of saving time, and I remember that the professors, at least during my time, did not go over the explanation. They just gave it to us at face value. This is the expression. This is how you're going to calculate the percentage error. What is m? M is the maximum value or the upper bound value of the second derivative of f of x, and in case of the Simpson, it is the fourth derivative of f of x. Here is an example of it, the calculating of the value of m, which you can then plug into m to calculate the percentage error. Percentage error at the end, it's going to be mostly a small number. 9 times out of 10 it's going to be greater than 10%. So you don't have to worry about that unless you made a mistake in solving of the Simpson and trapezoidal method. You can see that the percentage error is usually very small. And in this case, it's 0.00, like 0.08, the percentage, the mistake. Now, next lesson, improper integrals. What is an improper integral? It is an integral that has infinity. That's it. That's what they mean by improper. What does it mean? It means, and how do you solve it? You simplify it. This is, it might not make sense when the professor first explains it to you, but this is very simple. What you do is you take the integral and you turn it into a limit as the upper or lower bound of that limit approaches infinity. So from here, this should make sense to you. You're just taking an integral, but instead of, because we don't like infinity in the integration, we don't like to go to infinity, so we say instead of going to infinity, we'll go to b, and b of that in the context of that function approaches infinity or goes to infinity. Why does this work? This works because of the concept, because of how limits are laid out in the physical or in the mathematical world. The way that limits work, you can calculate the limit as it goes to infinity, but you cannot calculate the integral as it goes to infinity. So that is the whole premise of this lesson. It's just telling you that the integral, is either going to go to one of three cases. It's either going, one of two cases. It's either going to diverge or it's going to converge. Depending on what? Depending on this. Once you integrate it, if the value of p, or depending on the value of p in this context, if the value is equal to or less than 1, it's going to diverge. and if it's greater than 1, it's going to converge. What does this mean? It means that in a function, diverge means it's growing and growing and growing and growing and growing infinitely. There's no end to it. It's diverging away from the graph. So when it's going to plus or minus infinity, this can be the same thing. This can be also true for minus infinity. Doesn't matter. It's diverging away from the graph. It's growing more and more. Whereas with convergence, it is converging. It is closing down on an answer. It goes from what it can come in. It can come down from a very large number, but it has to approach as the value of x or b or whatever goes to infinity. It has to close in to a number or to a value. The value being, in this case, L. So this is a small graph to know if the function or the integral is going to go to infinity or to a number. If it's going to infinity, it goes to infinity, i.e. it diverges. If it is equal to 1 or less than 1, it diverges. In other words, it goes to infinity. And if it is greater than 1, so not including 1, greater than 1, it's going to converge. Easy as that. Now comes the fun bit. You're going to have a bunch of rules that you have to memorize again. Calculus has a lot of memorization, but it makes sense, and you're going to get into the rhyme of it as you solve a few questions. So here are just some formulas that you don't know what the value goes to if it converges. You just know that it goes to some value, some tangible, countable number. You can get to that number. So it converges. In this case, it's 1 over x to the power of 2. 2, if we go up, this is 1 over x to the power of p. 2 is greater than 1. You're a university student by now. You should know that 2 is greater than 1. So it converges. So it converges to some value. You don't need to know what that value is. You just know that it converges to some value. And p is greater than 3, it converges. These are all just some of the more common cases, in which case, these are some of the more common cases that you might have it expressed, but 99% of the time, it's just going to go back to this format, this formula, 1 over x to the power of p. Let's take this case. 1 over the square root of x. This is equal to 1 over x to the power of half. Same thing. So p, half, is less than 1. Shocker. So this is going to diverge. Same thing with x to the power of, so this is, you can express this as x to the power of half. So this is, and you can also express this as x1 over x to the power of minus half. And minus half is also less than 1, so this will also diverge. These are not, in this particular case, it's not something that you have to memorize, but you just have to understand and see that, yeah, all of these cases are just some confusing way of expressing this format. This is why this is the only formula given here, 1 over x to the power of p. All of these are just some of the most common cases in which it's a diverge or a convergence. So this is 1 over x to the power of 3 over 4. 3 over 4 is less than 1, therefore it diverges. Easy as that. Now, when you have a few cases of vertical asymptotes, which means that it is a value on the horizontal asymptote is a value of x that is never reached. So in this case, let's go for, let's say, red. So the graph can get as close to this value, but it will never actually reach that value. This is called the horizontal asymptote. There is a similar concept, but vertically speaking, which is when the graph approaches a value of y, but it never actually reaches it. Same thing. So in the cases where in your graph you have a vertical asymptote, you're just going to be using one of these formulas to simplify it and get to the answer. This is, sorry. What this is just the value from c to a of 1 over x, of 1 over x minus c, and then this is also 1 over x minus c. It's the same thing, but you are just splitting it at that point because at that very point you might have some graphs that are like this. Why are we splitting the integration from a to b? We're taking it as a to c and then c to b, because you might have graphs that are like this. In this case, you have, this is the y asymptote, this is the graph of 1 over x. This is an example of a vertical asymptote. You will, the value, the graph will never reach the value, it will never touch the vertical asymptote of x equals 0. Because you cannot pinpoint what 1 over 0 is. This is not something that has been proven yet. It is going to give you a math error if you put it on a calculator. So what are we doing here? If this goes from A to B, you cannot calculate it at this point, but you can calculate it at this point, and you can calculate it at this point. So what we're doing is we are splitting the integration to go from A to C. C is a value that we can calculate up until, but not including. And then again, you're doing it from C to B, not including C itself, because we cannot calculate it at C. And that's the whole premise, that's the game that we're playing here to get the answer. We're just like going around something that we can't go through. Like a mountain. You can't go through a mountain, so you're going around the mountain. So, the question is going to be phrased as investigate the convergence of. This does not mean that the graph converges. This does not necessarily mean that the graph converges. It just means tell me if it converges or diverges. So in this case, you have it as the integration of from 1 to 0 of minus 1 into 1 minus x. Now the question may be given like this, as 1 plus 1, or just 1 over. And what you can do is you can put these minuses in from yourself, so that when you differentiate this, you're going to get it as the numerator. When you differentiate this denominator, you're going to get it as a numerator. Why are we doing this? So that we can get this, because we know this value from 8.3, sorry, 8.2, no, 8.1. Integration by parts. This was one of the ideas that we covered previously. If you have the numerator on the top, that is the derivative of the denominator, it is just ln absolute value of that denominator. And since you added minus outside, you can keep the minus outside as well. And then you just calculate the limit from C as C approaches 1 from the left, because if you put 1 here, it's going to be whatever, some arbitrary number A over 0, and you can't calculate that because we just haven't all of the knowledge of math. We still can't divide by 0. That's the main rule that we have to abide by. And so we are splitting it so that we can avoid that as a question. So we substitute it, instead of as 1, we put it as 0.9999999, because like I mentioned in the graph example above, if this is your function, you cannot, and you want to calculate if it converges or diverges, if it approaches infinite or if it approaches a number, you can calculate this value from A till B, and this value, or the opposites, it doesn't matter really, at every point except at the point where the graph does not touch it. So in this case, it's 1. At x equals 1, or c equals 1, or whatever value equals 1, you cannot calculate it. So you calculate it from just before it to A, and then just barely after it to B, which is what we've done here. And that's the whole premise of the game. You're going to get a bunch of examples of it. This is one of the more fun ways to determine whether a function or a integral is a converge or a diverge, is you're just trying to express it as 1 over x to the power of p, and then you just see what the value of p is. Now, you have a few different tests to determine whether a summation converges or diverges. The first of which is the direct comparison test. So, the best way, you can memorize this is how it's going to be laid out in your textbook, but there is a different way to understand it, which is this way. Let's say that b of n, and they both have to be greater than 0. Let's say that b of n is this in green. If b of n diverges, and we know for certain, let's rephrase that. Let's say that b of n converges, and we know that for certain b of n is greater than a of n. And if b converges, then we know for certain that a also has to converge, because a is limited to being smaller than or equal to b, and we know that B converges, so A must absolutely converge. It cannot diverge, because then it would no longer be greater than. It would no longer be less than, it would be greater than. So since we know that B of n diverges, we know for certain that A of n also has to converge. And this is also true inversely. If the A of n diverges, and we know A is expressed in blue and B is expressed in green, if we know for certain that A of n is going to diverge, and we know that whatever B is, it is bigger than A, then we know for certain that A is also going to diverge. It cannot converge, because then it would be smaller than A, and that's just not true arithmetically. So that is why the cases in the rules are, if B converges, then A converges, and if A diverges, B diverges. This is called the direct comparison test. When you solve some examples in class, you understand this in terms of numbers. It also makes sense. If you don't know if this is something that, if I tell you, does the summation of, for example, does the summation of 1 over x to the power of 1 plus 1 converge or diverge? You don't know if this converges or diverges, but you know that, let's say this is B of n actually. You don't know if this converges or diverges, but you know that A of n, which is 1 over x to the power of 1, or integration, we agreed that summation and integration mean the same thing. We know that this, at x equals to 1, we know that this diverges, right? Because if you check up the rules, if you check the rules up above, at p equals 1, we know that this diverges. So if you go back here, we know that this diverges. We know that A of n diverges, and we know that A of n is less than it. A of n is less than B of n, because, well, B of n has that plus 1, so it's bigger. It's very slightly bigger, but it's bigger. So B of n is greater than it, and A diverges. So by the direct comparison test, we can conclude that B of n must also diverge, that this must diverge. And that is the idea behind the direct comparison test. Now, let's go over to the limit comparison test. It's kind of similar in the sense that you are comparing two limits, or you are finding the ratio between two limits, between two summations, let's call them, between two summations, integrations, whatever it is. You take, as n approaches to infinity, of A of n divided by B of n, if it gets you any number, any value, whatever value it may be, as long as it is positive, greater than 0, and as long as it is not infinite, as long as it is a number that you can count to, then either both of them diverge or both of them converge. Usually in the same case, you will know the convergence of one but not the other. So in the previous case, when I gave it as 1 of x and 1 over x plus 1, we don't know if this converges or diverges, but we know if this converges or diverges. And we use our knowledge on the convergence of this to determine the convergence of that. In the previous case, it was using the direct comparison test, but you will have some cases where it is easier for you to use the limit comparison test. Now, what is a sequence? Like we just said, a sequence is an integral. You need to differentiate between a sequence and a summation. A sequence is numbers separated by a comma, whereas a series is numbers separated by a plus. So you need to be able to differentiate between those two values, those two terms, let's say. So a sequence is an integral. 2, 4, 6, 8, 10, whatever that is, you can express that as 2 to the power of n. So 2 to the power of n, if n is 1, then it's 2. If n is 2, then it's 4. If n is 3, then it is 6. If n is 4, then it's 8, and so on. You will have some questions that are very fun, such as, what is the nth term is going to be phrased as this. That is, what is the nth term of this value? And you just need to find some formula, in this case 2n minus 1, n squared minus 1, to satisfy this condition. So, convergence and divergence. If you take the limit of any sequence, not series, sequence, the limit of a sequence, and it approaches a number, it converges. If it is plus or minus infinity, or it does not exist, then it diverges. There are a few cases in which case it's not going to be either. It's going to be 0 over 0. It's going to be some indeterminate value. Then you have to use L'Hopital's rule, which is you differentiate both sides, both numerator and denominator, and you will then get the limit and apply one of these two conditions. This lesson is simple, introductory. It helps in grasping the fundamentals of the next lesson, which is, this is just a page that brief notes, which is infinite series. Now, there are a few types of series. What is a series? It is the same thing as a sequence, but the numbers are separated by plus. So it's 2 plus 4 plus 8 plus 6 plus 10 plus 12 plus etc. So, when you are trying to find the convergence, or before we get to the convergence and divergence of an infinite series, let's define a few types of series. A geometric series is a series that increases by a factor of r. So, any number or any series that is laid as a plus ar plus ar squared plus ar to the power 3 plus all of that is considered a geometric series. This is, by the way, ar to the power of 1, and this is ar to the power of 0. So you will see that at every step, the power of r increases by 1. When you have a geometric series and you're trying to find r, you just divide, let's say these two, you divide any number by the number before it, so ar squared over ar, tick, 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 tick. This is the value of r. This is how you determine what r is in a geometric series. And this is how you express a geometric series as a summation. Now, with the divergence or convergence of a geometric series, you can express it as a to the power a divided by 1 over r. If this value converges, this value will converge if the absolute value of r is less than 1, and it will diverge if the absolute value is 1 or is greater than 1. And in both of these cases, you can see it's diverge. This will be the case of it. They are both diverge, but we're just letting you know that if r is equal to 1, it will not exist, but it will still be a divergence case. And if it is greater than 1, the absolute value of r that is, it is going to be plus or minus infinity, which is still considered divergence. Now, what is a telescoping series? A telescoping series, I genuinely don't know why it's called telescoping, but it is just a series in which all of the cases, all of the terms cancel except for the first term and the last term. So you're going to have it in this case, let's zoom in here. This case of 1 minus half plus half minus a third plus a third minus a fourth plus a fourth minus a fifth. All of these terms you can see will cancel out except the first term and the very, very, very last term. Now, why is this equal to 1? Because at the very end, if you keep going, plus 1 over 4 minus 1 over 4 plus 1 over 5, etc., etc., etc. These are all going to cancel out. At the very, very end, you're going to be left with 1 over its infinity, but we can't express it as 1 over infinity. That's not a finite value. We express it as 1 over 999999999, which is, for all practical purposes, equal to 0. So it's 1 minus 0, so it's 1. Since 1 is a value, since 1 is equal to L, a number we can count to, I hope you can count to 1, it converges. Now, you have something called the nth term test or the divergence test. These terms are synonymous, they both mean the same thing, which is just if you take the limit of a sequence, if you take the limit of a series depending on what that limit gives you, it tells you if it diverges or if it does not diverge. It does not tell you if it necessarily converges. So if the limit gives you a number or gives you infinity or it does not exist, then for certain that series diverges. However, if you take the limit of that series and it is 0, then you cannot definitively say that this series converges. You say that the test has failed. You cannot determine if it is diverge or converge if it approaches 0 or if the answer of the limit is 0. So you have to use a different test. What test do you use? You use the next lesson, which is 9.3, which is the integral test. The next 3 or 4 lessons are just all going to be tests to determine if if a series converges or diverges. So the integral test is just a test to determine if it converges, if the previous test failed, if the nth term test failed, which 99% of the time the nth term test is going to fail, it's going to be inconclusive. You're going to use the integral test. Integral test tells you that if the integral of a series converges, then the series itself converges, and if the integral diverges, then the series itself diverges, on the condition that all values of f of x, that f of x is positive, continuous, and decreasing. What does positive mean? If you substitute any value of x, you're going to get a positive answer. What does continuous mean? There is no disconnection at the graph, so it's not like, for example, f of x cannot be 1 over x, because f of 1 over x is discontinuous at x equals 0. And it has to be decreasing. What does decreasing means? Means that if you differentiate it, it has to be less than 0. So, because that is how you determine if a function is increasing or decreasing. If you have a function and you differentiate it, if it is at any value of x, if it is greater than 0, then the function is increasing, and if it is less than 0, then the function is decreasing. And that is how you determine if a function is decreasing or not. Here is an example. It's again, at this point you are just trying to play around these 3 conditions. You need to make sure that the function is positive, continuous, and decreasing. If all 3 conditions are met, then you can apply the integral test and find if the summation converges, then if the integration converges, then the summation or series converges, and if it diverges, it diverges. There's nothing else to this lesson. It's fairly straightforward, but you just have to solve a bunch of questions to get the hang and to get the grasp of it. Now, the next lesson is the comparison test, or there's a few different types of comparison. There is the direct comparison and the limit comparison. Now, the direct comparison tells you that if the series converges and it is greater than, this is going to be similar in concept to the point that we just went over, which is the, hang on a moment, the direct comparison test. We went over this actually. This is the same test. The direct comparison test is the same test that we went over in here at 8.7. This is the same test, direct comparison test. But in this case, you are applying it for a series, which is the same thing as it's the same thing as a summation. It's the same concept. So a direct series test tells you if that the bigger one diverges, then the smaller one diverges, and if the smaller one, if the bigger one converges, then the smaller one converges. If the smaller one diverges, then the bigger one must diverge as well. Which is the point that I forgot that I had written that. And now, what is the limit comparison test? It's also a very similar thing, which tells you that we don't know. This is the other point that I mentioned, x to the power of p plus 1. We don't know if this converges or diverges, but we know that, let's do 3 instead of p. We don't know if this converges or diverges because it's not one of the formulas, but we know if this converges or diverges. So we compare this to this, and if it's going to give us one of these 3 cases, where if you divide them by each other and you get a number, a tangible number, either both of them will diverge or both of them will converge. So in this case, if you are doing ax to the power of 3 plus 1 divided by 1 over x to the power of 3, these two will cancel and you are left with 1. So 1 is a number that you can count to, so either both of them will converge or both of them will diverge. And since we know that 3 is a case in which it will converge, then we will definitively say that the 1 over x to the power of 3 plus 1 will also converge. If it gives you infinity, then only if b is divergent, then a will be divergent. If b is convergent, then the test will have failed. And the same thing the opposite thing applies if the answer you get is 0. If b converges, then a converges. But if not, if b diverges, then the test will have failed. That's the whole premise. That's the whole premise of the lesson. There's no tricks about it. It's just you have to understand this. You should picture this to be able to understand it better, so that you can visualize it and understand why these are true. Now, with the ratio and root tests, there are two tests, and they're very simple and very straightforward. You can see it took half a page in my notes. The ratio and root test tells you that if the limit of a series, if you take a term and then you take the term and you divide that by a term before it, it's going to give you some value. If that value is equal to 1, then the test has failed. However, if that value is greater than 1, then the limit will diverge. If the value is less than 1, then the limit will converge. Why is that true? Why is that true? Let's say you are... What is happening with the screen? Let's say you are taking... these are points, sequence, but if you are adding them up, it becomes a series. So you are taking, let's say, this point and this point, and let's take, for example, this point and this point. If you divide the bigger term by the smaller term, because these are all lying on the y-axis, you are going to get a value in this case, and in this case, you're going to get a value that is greater than 1. So you know that if you keep applying this formula, then the function is growing. The series is growing, so it's approaching infinity, so it's diverging. However, in the cases where p is less than 1, this case is only true when the limit is getting smaller and smaller and it's approaching a number. But if you compare, let's say, this value with this value, you still don't necessarily know anything that happens in the blue area. You don't know if this is true. But if you compare these two blue values, the later one to the one before it, if you divide them, you're going to get a value that is less than 1. You know that this function is slowly going down. So if you approach it to infinity, if you keep it going to infinity, i.e. to the end of the graph, which you cannot see per se, then you know that it converges to some value, to some number. However, y is equals to 1 conclusive because it's like this. Because you cannot definitively say that this is going to converge or diverge. You don't know what it's going to be. It can be like this. It can grow. There are some graphs where it won't grow until after 600 terms, for example. And after 600 terms, it's going to grow to infinity. And there are some graphs that after 700 terms, it's going to stop at a number. It's going to go down and stop at a certain value. And it's going to converge. But you cannot prove that that happens if you take two terms and divide them by each other. Since both terms lie on the same axis, dividing them by each other, you're dividing the same value by itself. You're going to get 1. So that is not definitive proof to tell whether a graph or a summation or a series diverges or converges. Therefore, the ratio test will have failed. In this case, it is inconclusive. It's not enough proof for us to determine if it is true, if it converges or diverges. Same exact principle applies to the root test. The nth term of the summation or series is equal to p. If p is greater than 1, it diverges. If p is less than 1, it converges. If p is equal to 1, the test is inconclusive. Very simple idea, but you just have to understand why this is true. Now, with alternating series is some series with this magical, lovely term. What this term does is it just makes every other term negative or every other term positive. That's what it does. So you have some series, you have whatever series, let's say this is the series that you have, the one that we had in the first example. What the alternating series does, what this magical thing does to a series if you have it, so if this is 2 to the power of n times minus 1 to the power of n, the summation from n equals 1 to infinity, what this does is it makes this such that this is n minus 4 plus 6 minus 8 plus 12 minus 12 plus 4 plus what's after that? What is it? No, it's doubling. Plus 20. No, it's not doubling. Yeah, it's doubling. Is it? No. Plus 12 minus 14 plus 16 minus 18. It's just going back and forth between positive and negative. But the terms follow a formula, follow a sequence, they follow a pattern, which is 2n. It's just that the sign changes, the sign alternates. And that's very simply put what an alternating series is. Now, alternating series are a bit tricky because you cannot determine if it's going to converge or diverge, because on a graph, alternating series look like this. So you don't know if this diverges in, for example, this case. This is diverging. However, you're going to have some cases where it converges, like this. They're both divergent. They're both alternating series. One of them converges, the other one diverges. So how do you determine that? This is how. So, to prove whether an alternating series is convergent or divergent, you do the alternating series test, which says that you can ignore the minus 1 to the power of n, and you focus on the u, or on the other part of that series. If u of n satisfies all three conditions, then then the series converges, otherwise it diverges. So, what does that mean? Let's see here. If all of the terms of u of n are positive, and u of n as a function is decreasing, which, as we agreed, that f of x is less than 0, the derivative of f of x at any value of x is less than 0, and the limit of just u of n goes to 0, then it is convergent, otherwise it is divergent. Then the alternating series is convergent, otherwise it is divergent. So, if there's three conditions when you apply this test, there are three conditions that you can determine the answer of. It is either going to be absolutely convergent, conditionally convergent, or divergent. It is absolutely convergent if a of n is convergent and the summation is convergent. It is considered absolutely convergent. If a of n is divergent but the summation as a whole is convergent, then we consider it as conditionally convergent. So let's do it as if this is convergent but this is not convergent, then it is conditionally convergent. And if neither are convergent, then it's just divergent. That makes sense, hopefully. So that is the conditions under which you determine if it's absolutely or conditionally convergent. Otherwise, it's just divergent. Now, let's come to the least fun part of the series lessons. So the series are like everything after 9.1. And you can include 8.7 as well in that. Now, power series are a way to determine if a series is convergent or divergent, determined based on what you know from another series. What does that mean? So, you have this series, right? You have c of n times x of n. If you spread this out, you can see that this is just c of n times a to the power times x minus a to the power of n, and we know that this is just a geometric series where with a. So this is, in this case, it's a equals to 1. So this is a. So now this becomes a to the power of r to the power of 0, a r to the power of 0, a r to the power of 1, a r to the power of 2, etc., etc. So you are using a series that you previously knew to unlock it. That series is the key to unlock your knowledge of whether or not the new series is convergent or divergent. Now this lesson, very frankly, it's a bit confusing, and I believe that the best and most clear way to describe it or to explain it is with the Organic Chemistry Tutors video of power series. One moment, please. This video here, I'm going to defer this particular lesson to the organic chemistry tutor. He's absolutely incredible at explaining this particular lesson. There are a few videos that you can watch, power series, but they're all very helpful. Once you've understood the concept behind the power series lesson, you can come back here and use this as just a reference. If the limit of the absolute value of the ratio test is 0, then this will all make a lot more sense when you have watched the organic chemistry tutors video. And this is going to be the answer. The answer is always it's going to be long. The answer is always going to be long. It converges for all values, the radius of convergence. This, trust me, this is going to make so much sense after you watch the organic chemistry tutors videos. He explains it in a way that I just simply and humbly put, I cannot explain it as adequately as he can. I have here mentioned a few, an example of it. This is the summation from n equals 0 to infinity of x to the power of n divided by n factorial. We use our previous knowledge, using the keys that we just discussed, to find the answer. And since here we found that the answer is equal to 0, and from the previous slide we know that if the limit of the power series approaches 0, then we say that this converges. Okay, it converges for all values of x, and therefore the radius of convergence is infinity. The interval on which it is convergent is I minus infinity to infinity. You can check the interval. This is how you check what the interval is. If it is not minus infinity to infinity, you check the endpoints. You solve that series to check the convergence to make sure that it's convergent. And if it is convergent, you include it in the interval of convergence. So you're going to have eventually, like, this is your interval. The radius of convergence is going to be, for example, here. You need to solve it at these points to know if you're going to include these points in your interval of convergence or not. And your radius of convergence, or the radius, is just going to be half of that point, just so you know, in the future. That's why r is infinity, so from 0 to infinity, and the interval is minus infinity to infinity. This lesson is going to make so much more sense after the organic chemistry tutors videos, trust me. So, let's get to something that is very similar to the keys, but frankly explained in a bit of a nicer way. The Taylor and MacLaurin series. Taylor and MacLaurin series are, it's basically the same concept of a Taylor series, but the only difference is that it's MacLaurin series when c is equal to 0, and I'll explain what the hell c itself is in just a second. Pardon my French. So, when you have a function that is expressed as f of some value c multiplied by x minus c to the power of n divided by n factorial, this is going to be your function. And the function is going to be the summation of the derivatives of that function. So it's going to be always, it's going to take a lot of solving. This lesson is you should get ready to use a lot of ink or graphite, because you're going to be finding at the very least the fourth derivative of a function. because it's always going to be in this formula. It's always going to be in this format, f of some value c multiplied by x minus c to the power of 0. In this case, since it's power of 0, you can just cross it out, you don't have to include it. 0 factorial is 1, 1 factorial is 1, you also don't need to include them. But this is just to show you that there is a pattern here. Show you that the pattern is always n here and n here, n factorial in this case. So since n starts from 0, 0 to the power, something to the power of 0 is 1, and 0 factorial is 1 as well, so they're not included. The function can also be rewritten as this, just like because this is how the professor is going to write it, but the professor writes it in a way that it's harder to see. It's hard to see the pattern in it. So if this is how it's written, it doesn't make much sense what the pattern is, but once you realize that in reality this blank here is just 1 factorial, and this is 0 factorial, and this is x minus c to the power of 0, you see what the pattern is, and it's easier to understand what is actually happening. So how do you solve? You solve this by taking, at the very least, the fourth derivative, and you are finding some summation that is equivalent to them. And your final answer is going to look like this. This is the function, so all of this is f of x, so all of this is all of this. It's going to be equal to some summation. This is going to make a lot more sense once you see, at the very least, an example. You use a previously solved series to solve another one. That's the whole concept of keys, and there's one of the fun properties of series and integration specifically is that you can integrate a series. If you integrate a series, and the series is a0 plus a1 plus a2, it's the same thing as if you're integrating every individual terms. That is one of the properties of series. So let's take an example. Find the MacLaurin series for sine of x. So since he asked for the MacLaurin series, we know that c is equal to 0. So in this case, we don't include c in our calculations. So f of x is sine. Differentiate it once, differentiate it again, differentiate it again, differentiate it one more time. You get this set of answers. And now put x equals 0 of all of them. You get this set of answers. So once you plug them into the formula, these three triangles mean therefore. Therefore, sine of x as a function is equal to 0 times x of 0, 0. You're crossing this out, you're crossing this out, you're crossing this out. And something you'll notice is that it's going to be alternating, where every other term is 0, and every other term is an alternating 1 in terms of value, 1 and minus 1, 1 and minus 1. So after you've simplified it, it's going to be 1 minus 3 plus 5 minus 7 plus 9 minus x11 plus x13. And all of them are divided by the factorial of the exponent. So this is going to be times 11 factorial, and this is going to be divided by 13 factorial. That's not 13. That's 13. That's a weird looking 13. That's a better looking 13. So, how can we express all of this as a summation? Well, first step is we know that it's alternating. We know that it's plus minus, plus minus, plus minus. So we include the plus minus in it. And we know that there is an x in every term. So we include x as it is. And we also know that the terms are always even. So the best way to write something that is always even as 2 of n, because this guarantees, the terms are always odd. The best way to guarantee that you will always get an odd number is 2 of n gives you always 2 of n is going to give you an even number. So 2 of n plus 1 always is going to give you an odd number. Try it. If you don't believe me, try it. 2 of 3 is 6. 2 of 2 is 4. 2 of 4 is 8. These numbers are always going to be even. So if you add 1 to each of them, this is going to be 5, this is going to be 7, this is going to be 9. You're always going to turn out with even numbers. This is just a pattern that you have to see in math. This is just the way that math is laid out in nature. So that is how you can guarantee an odd number every time and if you do it as 2n plus 1, you have to start with n equals to 0, so that at the first term is just going to be x to the power of 1, and then it's going to go to 3, 5, 7, 8, 9, 11, 13 till infinity, because you're going to infinity. And then you use the same thing in the denominator as a factorial to get it as this answer. I'm spending a lot of time on this because you need to understand, because this is going to be used as one of the most common keys in this lesson of sine. The key for sine, this is now, you have just unlocked the key for the function f of x is sine of x. Now, find the Maclaurin series of cosine of x using the Maclaurin series of sine of x. So, we know that, and this is something that's very neat about, that I just discussed about series and integration. We know that the derivative of sine of x is equal to cosine of x, right? We all agree on that from 1.3, and we're at 9.8 right now. So if we differentiate this, then we will get cosine of x, right? So we just have to differentiate this monstrosity. But this monstrosity is actually very easy, because what are you differentiating? You're differentiating with respect to x. So we can ignore n. We can ignore n here. We can ignore n here. We are differentiating with respect to x. So how do we do that? You can differentiate it as you can express it as it is in this long form and differentiate every term. You will be left with this, which is x to the power of 2 over 2 factorial plus 1 minus x to the power of 2 over 2 factorial plus 4 plus x to the power of 4, etc., etc. Or what you can do is you can differentiate this term here, and this is the much easier and simpler way, is if you differentiate this expression, this expression with respect to x 2n plus 1, differentiating this just gives us x to the power of 2n. Is that not true? This is how you're differentiating it, because this is x to the power of x times x. So you're just differentiating it normally. So you're left with this as your answer. And since you know, as someone who has solved the Maclaurin series for sine, you know that whatever is raised to the power of whatever x is raised to the power of 2, it's going to be the same thing as the factorial for it. So this is how you're solving the Maclaurin series of cosine of x using the Maclaurin series of sine of x. You can differentiate each term individually, or you can differentiate the function as a whole. Both answers are going to be considered correct. And this is the point that I mentioned previously, which is the fact that these terms don't have x in them, so they are constants. They are considered constants, at least, let's say. Thus concludes the lessons for series. Now let's get into the last 2 lessons in all of Calculus 2. These lessons are very simple, very straightforward, but they require a new type of thinking. This lesson just requires a new type of thinking. That is the main difficulty of this lesson, is just that it requires a new type of thinking. Now, this is a Masarani memo. When you are thinking of a graph normally, you think of it as a function of x and y. You're thinking of it as a graph with respect to x and y, with them being related to each other. So y, in this case, y is some function of x, and x is some function of y. They are always codependent. With parametrization, you are breaking that gap of y is f of x. You are breaking that gap and saying that y is f of t just as x is f of t. But this bridge does not exist anymore. So they are both connected to a function of t, but not connected to each other. Let's graph that so that it makes sense. So this graph is just another normal graph, but if you want to express it as a function, you're expressing the x function as a value of t, and you're expressing the y function as a function of you're expressing the y value as a function of t and the x value as a function of t. That's genuinely the whole lesson. This is not a joke. That's genuinely the entire lesson. 10.1 is just you playing around with formulas to get a graph, to get a something that you can graph in terms of t. That's it. This lesson is so simple. It is so easy, but it just looks a bit scary. It looks a bit confusing because it needs a new type of thinking. You have to break the previously established cycle of thinking that x is a function of y and y is a function of x. Now, x is a function of t and y is a function of t. X and y no longer depend on each other, but they both depend on a new variable, t. That's the whole thing. Now, let's play around a bit. So, you have x is equal to t cubed, and you have y is equal to t squared. Find the derivative. But you are finding the derivative with respect to t, because that's what we want. Because we're talking about stuff in terms of t. So you're finding the x over dt, and you are finding the y over dt. This is another way that it can be expressed. dy over dx, this is the function that we are normally used to, but since dy is in reality dy over dt, because it's with respect to t, and dx is dx over dt, you get it as such. If they want you to find the derivative as in dx over dy, you know that since the derivative of dy is equal to, in this case, it's going to be equal to 2t dt, this is what dy is going to be equal to, you just have to think of it now as terms of t instead of as terms of dx and dy. That's genuinely the entire lesson. There's nothing else to it. The second derivative formula is just going to be the derivative of dy over dx divided by dx, all with respect to t. That is all there is to it. You may be asked to graph have some questions graphing with respect to dt. The same thing that we took previously, all the way over, where was it? Arc length was 6.3, I believe it was. Yeah, 6.3, arc length and surface area, and the lesson just before that, the methods and volumes and all of this, you were thinking of x and y as values that depend on each other, so you are finding with respect to f of x, dx. The only difference is that now you are finding them with respect to dt. dt. That is the whole lesson. You have now finished all of Calculus 2. The best tip I can give to students, if you are watching this before a big test, before your midterm, before your final, solve as many questions as you can. I hope that I was doing a good enough job with explaining the ideas behind the lessons. The purpose of this video, as was expressed in the beginning, it was never to solve questions and practice problems. It was just to explain the idea behind the lesson in case you didn't understand it from the professor, so that you can know how you're solving. Because if you are just solving like a robot, you just know that this equals that and therefore we need to do that, then in the test, if you are stumped or if you have a question that you have not memorized, you're going to face some difficulties. So my hope with creating this video is that I help some students understand the idea behind the lessons in Calculus 2, because you're also going to be building on this in Calculus 3 and then in the future in whatever major you're going into. My purpose is to help students understand the essence of the lesson, so that when they solve practice problems, it's going to be easier for them to solve because they understand they're solving. And that is the essence of what a university should be and what a course should seek to do. It should seek to explain to you how this is true or why this is true. I didn't want to go into too many details with proving each formula, but I would strongly recommend that if there is a formula that you are not convinced of why this should be true, or if you don't see it, so to speak, if you don't see how this becomes that, then seek out the proof. Go to your professor's office hours. They are very helpful with this and they would be more than happy to oblige you during office hours, or you can look it up online. You have lots of great resources online, such as the Organic Chemistry Tutor, 3 Blue 1 Brown. There are a lot of really good teachers online that would be more than happy to help you understand it. And with that being said, I genuinely hope everyone does good on the Calculus 2 finals and midterms. Hopefully you guys can do better than I did when I performed my Calculus 2 finals. And yeah, thank you so much for watching, and best of luck. Thank you so much. Have a nice day.